Evening. I'm spot on weather meteorologist Matthew Euler. Welcome to my latest training video. Now, in tonight's training video, we're going to talk about the wave cyclone process. This is involving the process, the stages of a mid-latitude cyclone. And so we're going to cover this in depth tonight. But first, before we get into the wave cyclone process, I promised this for my last training video. I promised that I would show you the chart that kind of breaks down some of the topics we've discussed previously. And some of those topics included vorticity, vorticity advection, thermal advection as well. And so we kind of mentioned about, what does vorticity, different types of vorticity advection do as far as rising and sinking air motion in the atmosphere. Positive vorticity advection is an indicator of upward or rising air motion in the atmosphere. Negative vorticity advection is an indicator of downward vertical motion or sinking air motion and nice weather in the atmosphere. And then you have this thermal or temperature advection, whether you have colder air moving in or warmer air moving into an area. And so this was a chart that I pretty much memorized when I went through meteorology school. And I'm going to break down a few points of this chart here before we move into tonight's training topic. Okay, so if you look at this far left-hand column here, this is showing you the different types of vorticity advection. Vort, ADV stands for vorticity advection. And we have different acronyms or terms here, abbreviations I should say. PVA is positive vorticity advection, NVA is negative vorticity advection, and then just the plain word neutral represents neutral vorticity advection. And there may be cases, specifically in the summer season, remember, where you really don't have any type of vorticity advection, right? Because your vorticity gradient and your pressure gradient, your thermal gradient is all that is so weak in the summertime. Column 2 shows temperature advection, TMPADV, and this is going to show you CAA is colder air advection with cold air moving in, WAA is warm air advection, and then, maybe you have cases where you don't have any temperature advection at all. And then what are the effects of vorticity advection and these thermal or temperature advection on my upper level heights? Down arrows indicate that the upper heights are falling or lowering. The up arrows indicate the upper heights are rising. And then if you notice on this neutral row here, there's absolutely no change to any of it. In a couple of these cases when you have, for example, neutral vorticity advection, no temperature advection, you really don't have any change to any of these parameters. We also have a column for surface pressure. Down arrow indicates the surface pressure is falling. A up arrow indicates the surface pressure is rising. Then we have a column for vertical motion. Whether we have an up arrow, it's upward vertical motion, rising air in the atmosphere in the vertical. If you have a down arrow, that's sinking air motion, okay, downward vertical motion. And then we have stability, a column for stability. If I have a down arrow, that indicates the stability is decreasing. An up arrow, stability is increasing. And then we have clouds. Are the clouds going to increase with the up arrow, or are they going to decrease with the down arrow? And finally, we have the adiabatic process over here in the far right, this column. And this represents, with rising air motion, for example, upward vertical motion, we'd have adiabatic cooling going on. If we have sinking or downward vertical motion, we have adiabatic warming. So this is a nice chart that kind of encapsulates everything we've talked to this up to this point on the training series from this particular summer. So let's just look at a couple combinations here. What happens if we have positive vorticity advection, PVA, plus warm air advection, WAA? What's this going to do to my upper heights? Well, we really don't know, because with warm air advection, it's generally going to cause my upper heights to rise. But perhaps we have an offsetting effect with positive vorticity advection. Upper heights might try to fall, for example. So we don't know. Whenever you see the question marks on this chart, you just really don't know the answer. You'd have to analyze other factors. But what happens if we take NVA and cold air advection? Well, that's going to result in rising surface pressure, because NVA is an indicator of downward or sinking air motion. Cold air advection means my air mass is heavier. So my surface pressure is going to rise in this case when I combine negative vorticity advection, NVA, plus cold air advection, CAA. What happens if I take NVA and cold air advection? What happens to my vertical motion? It's going to be downward in the atmosphere, downward vertical motion, sinking air motion. My stability is therefore going to increase, and my clouds are going to decrease. When I have sinking or downward vertical motion, the air is going to warm adiabatically and it's going to dry out. What happens if we have, let's do one more combination, I'll kind of show you how this works. So let's go back to PVA and warm air advection, okay? We didn't really know what was going to happen at upper heights. We'd have to analyze the height tendencies. But what happens if we take PVA and warm air advection? Surface pressure is going to fall. Why? Because PVA is an indicator of upward or rising air motion in the vertical in the atmosphere. Warm air advection is going to result in less dense air, so that surface pressure is going to fall. Now, the vertical motion is going to be rising air motion with PVA plus warm air advection. And then stability will decrease because we have that rising air motion, an adiabatic cooling process. And then we're going to increase our clouds. When we have positive vorticity advection, PVA plus warm air advection, our clouds are going to increase. So these can all be combined with each other. Different types of vorticity advection plus different types of thermal or temperature advection. And then we want to analyze what it's going to do to our upper heights. We want to analyze what it's going to do to our surface pressure, vertical motion, whether it's rising or sinking air motion, stability, whether it's increasing or decreasing, and the clouds, whether they're increasing or decreasing. And what type of adiabatic process is it? If we have neutral vorticity advection and no temperature advection, we get no change to any of these parameters. Another case where we get no change is we have neutral vorticity advection plus no temperature advection. Again, no change. So in general, this is a nice chart. It's a summation to kind of think about, hey, what happens when I have these different combinations of vorticity advection and temperature advection? All right, so now let's go into tonight's training. Hopefully that last slide was a nice review of everything that we've covered up to this point. With the overview in tonight's training, we're going to look at a hypothetical versus the real Earth. And then we're going to examine these frontal waves. Stable wave, we'll look at the stable wave, we'll look at an unstable wave, we'll look at a mature wave, and then we'll look at the decaying wave. So let's take a look at this hypothetical Earth. Before we get there though, we must realize one thing. We have differential heating effects across the latitudes from the equator to the polar areas. Now this graph on the right shows your surface temperatures. This is in degrees Celsius, okay? And it shows the average surface temperatures actually over a 365 days, so basically a year. The orange coloring indicates your warmest temperatures on average, okay? And that's of course right along the tropical areas of the world, or along the equator and a little bit north and south of that. And then as we go northward or towards the poles in either hemisphere, it could be the northern hemisphere or the southern hemisphere, you notice how these colors become cooler looking, like the aqua color and the blues and the purples. This is indicative of cooling temperatures as we go poleward in either the northern hemisphere or the southern hemisphere. The scale is of course right here at the bottom for your surface temperatures in degrees Celsius. So you can clearly see that the purple colors are indicating -10 degrees Celsius in colder temperatures. And then if it's an orange color around the equator and the tropics here, that indicates temperatures anywhere from 25 degrees Celsius, which is 77 Fahrenheit, and then warmer. So we have this differential heating across the latitudes. These low and high pressure systems are created, and they're developed because of this temperature imbalance from the differential heating across the latitudes. Hottest air over the tropics, coldest air over the poles. This difference in heating is the driving force that causes these wave cyclones to develop, these mid-latitude cyclones. Now, if we were to look at a hypothetical Earth, for example, what would we see? Okay, so let's just say we have all water. There's no land on the Earth. It's just all one uniform surface. It's water. There's no land masses on the Earth, okay? What's going to happen here? Okay, so this is our stationary front. I'll go ahead and circle it here so you can see it better. This is our stationary front in the northern hemisphere, okay, because this line right down the middle, the solid black line, represents the equator at 0 degrees latitude. This one right here. And we have another stationary front here in the southern hemisphere, okay? Now these dashed red lines indicate your lines of equal temperature, isotherms. Notice how your lines bunch up poleward or to the north of the stationary front in the northern hemisphere, and then it'd be south, because in the southern hemisphere, as we go south, we get closer to the South Pole. So we have the tighter temperature gradient, generally going to be in association poleward of either of these stationary fronts, okay? So on a homogeneous planet, there would be no north or south movement of air. This is the bottom line I'm trying to get across. This is all water. A wave is a weakness in the polar front caused by the cold air pushing south, warm air pushing north. But on this homogeneous planet, there would be no north or south movement of air. Everything would generally be in balance already. We'd have cold air. I'll put a letter C up here at the polar areas in the northern hemisphere and the southern hemisphere. You'd have cold air at the poles, and then you have warm air. I'll put a W down here at the equator. Polar front would divide the cold and warm air masses in this straight line. However, the real Earth, we have land and water distribution. We have land masses, right? And these land masses and this water is going to heat and cool much differently. This causes that difference in heating, okay? Now, the atmosphere is in a state of constant change or flux, constantly trying to maintain balance. Colder air is trying to get warmer or move south, while warmer air is trying to get cooler and move north. As this transfer of heat via temperature advection takes place, it causes these bulges or waves to form along the polar front. Now, if we look over here on the right, notice how I don't just have a stationary front going west to east. On the homogeneous Earth, I now have waves. I have waves of low pressure that are forming along this boundary in multiple locations. This is the polar front. The polar front usually resides at about 60 degrees latitude, and it's the convergence of the warmer westerlies, the warmer westerly wind belts, and the colder polar northeasterlies. Okay? So you get convergence of cold and warm air constantly battling it out. You get these waves of low pressure to form along these stationary boundaries, and the job of these low pressure systems is to redistribute this heat northward, redistribute the cold southward, so things kind of balance out. All right, so what exactly is a frontal wave? It is a weakness in that polar front that we just talked about in the previous slide. The weakness must exist for a wave to form. Now, if you need to go back and review my last set of videos, please feel free to do so, because I talked about Pedersen's rule, which described the conditions necessary for this weakness to develop along the polar front. All right, so remember the three key ingredients we are looking for Pedersen's rule. We're looking for a strong thermal gradient, we're looking for weak temperature advection initially, and we're looking for a weak pressure gradient. So for frontal waves, initially we get that stationary front, that polar front. It's present, or we can even have a slower moving active cold front. Waves then can develop along this stationary front or on that southern or western portion of a slow moving active cold front. And you get wave initiation, which will begin when some other parameter interacts with that stationary front. What could that parameter possibly be? Well, there's a couple cases here we can give examples. There's a couple examples here for the necessary parameters to kick off a surface area of low pressure. The first would be upper level divergence. So we get divergence. Now, remember this, okay? Let's just say this is at 500 millibars. We talked about this extensively. We talked about short waves, right? We talked about how they interact with these surface fronts and develop these low pressure systems along the fronts. So if this is this solid dark line here, right up here, the solid dark line represents your shortwave trough axis. Remember that divergence aloft is going to occur out ahead of the shortwave trough axis, okay? That's that pink magenta color here. And notice how that PVA, or divergence aloft, is directly on top of this wave as it develops at the surface. So we have a black L, which represents your low pressure. We got an area upper level divergence. Upper level divergence, that chimney effect, is going to basically result I'll go ahead and draw it down here in the bottom right, is we're going to have stronger upper level divergence at 500 millibars, or removal of mass to the air column, than what's coming in at the surface. So again, the magnitude is represented by the arrows. Notice I have shorter arrows at the surface. Here I just circled. I have larger areas, or I'm sorry, larger arrows, if I can speak, removing mass aloft. Greater magnitude of mass being lost aloft is going to increase my upward vertical motion, resulting in storminess, clouds, and precipitation, an area of low pressure to develop along this frontal boundary. All right, so, and we have, initially what we have is we have warm air moving north, okay, with this warm front, and then we have cold air moving south. So we're trying to get that balance within the atmosphere of the air masses. Warm air moving north, cold air moving south. We're starting to get that temperature reduction, right? Because the interaction of this major shortwave trough at 500 millibars and the upper level divergence is going to kick off this wave of low pressure to develop along this frontal boundary. All right, so now let's kind of break down the difference between stable and unstable waves. Now, stable waves are going to form as a result of the atmosphere trying to balance itself. And at some point along a stationary boundary, the temperature difference causes the warm air to push north, the cold air to push south. This creates that wave on the front. Another cause for wave development at the surface may be the flow around the frontal boundary. You may have wind on either side of a stationary boundary parallel to each other, but if the pressure gradient increases on one side of that front, the frontal boundary will respond by pushing poleward or equatorward, resulting in the formation of a new wave of low pressure. Now, with these stable waves along these fronts, stable waves do not have upper level support. No major shortwave trough in the upper levels is there to create the divergence aloft or the low level convergence. So with stable waves, you don't have that, that area PVA and the upper level divergence out ahead of that shortwave trough aloft. You don't have the upper level support in the form of that major shortwave. Surface low pressure is very weak. Its associated weather is confined to a smaller area immediately around that low pressure center. So not all waves that develop along these frontal boundaries are unstable. There are some cases where you just get a stable wave and it's much weaker. With stable waves, all stable waves do not necessarily transition into unstable waves. They simply remain on that frontal boundary as a wave, and they may transition back into a stationary front when the conditions warrant. Now, some stable waves do transition to the next stage in the wave cyclone process, and this would be the unstable wave process. So now we're going to take a look at the unstable wave process. With unstable waves, they're going to undergo cyclogenesis as a result of a major shortwave trough aloft. So there's a connection from the surface stacking back to the colder air aloft. All right, so for example, we have a major shortwave trough. Maybe it's at more than one level. We have one at 700 millibars. We have a reflection up at 500 millibars. And that area of upper level divergence, PV, out ahead of the shortwave trough axis begins to interact. That divergence aloft ahead of the trough axis interacts with the surface low. It goes from a stable perhaps to an unstable wave due to strong surface convergence and the deepening low. With unstable waves, they generally move slower than stable waves. Why? Because the amplitude is going to be much larger. You remember we talked about amplitude with long waves and short waves. One big takeaway we talked about in those previous training videos is when you have a wave that looks like this versus a wave that looks like this, okay? This one is deeper. Notice how deep this one goes, this U shape. It extends much deeper in amplitude. Therefore, this is going to move slower, all right? As compared to this one on the right, where we have much less deepness or amplitude to this trough, this is going to move faster. So I'll just put a letter F here, right? So it's the same thing with unstable waves. They're going to move slower than stable waves because the amplitude is much larger in association with the unstable wave. So a slower movement. Now, as the low pressure intensifies at the surface, the cold air pushes farther south and the warm air pushes farther north. And then you get these clouds and precipitation form associated with unstable waves. It covers a very large area, specifically in the fall and winter time. You really will see a lot of cloudiness that extends over greater distances in the wintertime, specifically with these unstable waves, these mid-latitude cyclones. You definitely get the clouds of precip, especially out ahead of the warm front. Right there where, with the warm front, let me just show you down here at the bottom. So with the warm front, what you have going on here, okay, let's just say this is your warm air, okay, this is W, warm air, and it's moving up and over colder air at the surface. This gently gliding slope with the warmer air moving up over the colder at the surface is going to result in an extensive area of stratus clouds and most likely continuous precipitation before this warm front actually moves through your area. Okay, it could be rain, it could be snow, continuous steady light rain or snow. That's very common ahead of warm fronts when you get this isentropic upglide, this warmer air moving up and over the colder air at the surface. With unstable waves, satellite imagery is a great tool to identify them. It helps to identify them by locating a feature called the baroclinic leaf. I'll show you an example of that baroclinic leaf on the next slide. But basically what it is on satellite image, if you're looking at a weather satellite image, it's a sharp, well-defined edge on the cold side of the cloud system. This sharp edge outlines the polar front jet stream and may take on an S-shaped curve. You'll see this in the cloud pattern. It's very extensive and takes on more of an S shape. And I'll show you an example of what that shape looks like in a minute. Now you'll get a vorticity maximum, that vortmax we talked about in the vorticity training videos. That vortmax is approximately 1 to 3 degrees back in the colder air at the inflection point of the S-shaped leaf. Now, a lot of foreign language here, right? I'm going to break this down in a minute, and that's the slide I'm going to break it down on. Bear with me for a moment as we go through these words. So the vorticity maximum, vortmax, indicates an associated major shortwave trough. The coldest cloud tops are going to be downstream from the shortwave trough. They're going to indicate where you're having that greatest rising air motion, the divergence aloft. It's also going to be a very good area where you're going to place your surface low pressure system, your wave, your surface wave. Now, as the unstable wave intensifies, the frontal systems associated with it are undergoing frontogenesis. We talked about frontogenesis. It's the development of a front, or it's the strengthening of an existing front. And how do you do that? Because you got greater temperature contrast on either side of the front. Those isotherms, lines of equal temperature, are getting more close together, more tightly packed. And that indicates a stronger frontal system at the surface. That's a frontogenesis process. Now, the lifetime of unstable wave is going to vary, but as long as the upper level short wave remains linked with the surface low, it will progress into the mature stage. Let's take a look at some of these pictures now. Hopefully you'll understand it better, okay? Picture on the left, we have our black solid line. This is our trough axis here. We have an unstable wave at the surface. See this black L? See the frontal boundaries here? We have the red semicircles on the same side of the line. That indicates a warm front. I'll put a W there. And then these blue triangle lines coming south and southwest out of this low pressure or this wave along the frontal boundary. This is a cold front. I'll mark this blue line as a C. So we have cold air moving in from the northwest. We have warm air moving in, basically cold air moving in from the northwest. And we have warmer air moving in from the south. And then we have this shortwave. I'll just label it SWT for shortwave trough at 500 millibars, okay? And out ahead of the shortwave trough, look at the linkage. See the black arrow here between your surface wave, your low pressure, and the upper level feature, the major shortwave trough. Unstable waves are going to be linked to these upper level features, and you're going to get your area of PVA, or upper level divergence, directly above, superimposed over the frontal boundary, over that low pressure as it develops. When we talk about the middle diagram here, we're talking about that baroclinic leaf on a satellite image. It resembles more of an S-shaped pattern here. And the inflection point is going to be kind of like that medium point where you have straight line flow with the winds. And you typically going to get a vorticity maximum. I'll make it a red X, because that's what you would see on the 500 millibar vorticity chart. That red X represents your vorticity maximum, and it's about 1 to 3 degrees. 1 to 3 degrees, what do we say on this? 1 to 3 degrees back in the colder air at the inflection point of that S-shaped baroclinic leaf. And there it is, vorticity maximum, okay? So you're going to get a wave of low pressure to develop here at the inflection point, and you're going to get that link back to this vorticity maximum, positive vorticity advection ahead of the shortwave trough with the vort max, and you're going to get rising air motion. If we look at this diagram on the right, the solid dark arrow represents the PFJ. What does that stand for? That's your polar front jet, all right, this dark solid line. And this again is your S-shaped curve. If you look at satellite imagery, this would be like your S-shaped curve pattern, okay? So that is going to represent your S-shaped curve. This is your inflection point here. This is where your wave of low pressure would develop. And you got your upper level winds associated with the polar front jet. And in some cases, you get the quadrants of the favorable rising air motion quadrants of that jet. You get a jet maximum in here associated with the PFJ, polar front jet. Remember this? I did this on a previous video. We talked about jet stream maximum. And if you're in that left front or right rear quadrant, LF, left front, or the right rear quadrant of the jet max, where you have these accelerated regions of wind speeds within the jet core, you could easily kick off a wave of low pressure at the surface here associated with the baroclinic leaf. All right, so we get the unstable wave. Now we're going to advance in intensity. We're going to move into the mature wave stage of this wave cyclone. Now this is going to occur where you get the frontal occlusion process beginning. Okay, so this line over here, right here, this, where you have these dark semicircles and these dark triangles on the same side of the line, this represents an occluded front. Now, let me go ahead and label these fronts for you. Okay, so what I just circled is the occluded front. I'll put that as a letter O. This coming out of due east out of the low, I'm going to put a W next to that because that's the warm front. And then coming south to southwest, extending south-southwest out of this wave of low pressure, the mature wave, I have a cold front. I'll represent it by a letter C. So as soon as you get the occlusion to take place, this, when it begins, this then becomes a mature wave. See this black L here? This black L is kind of at the intersection of all three fronts, right? It's at the intersection of the occluded front, represented by the letter O, at the intersection of the warm front, W, and also the cold front, C. And we call that the triple point. Where all three fronts meet is known as the triple point in meteorology, okay? We have a wave cyclone developed along the triple front here, right here, and it's going to an intensification stage. This is the mature wave stage. We got an occlusion that just began, and the process has begun. Surface low deepens to maximum intensity at this point, and a boundary between three different air masses is established as a result of cold air catching up to the warm air. This is an example of a cold type occlusion because colder air is catching up to warmer air at this point, and that's what's forming this occluded front. Again, the intersection of the three different air masses is going to be called the triple point, and that is represented right. Triple point is going to be this point right in here, where all three fronts meet. With the mature wave, how do you identify it in satellite imagery? You can look at the mature wave by the presence of a comma cloud. Comma cloud has very distinct parts on a weather satellite image. It has a baroclinic zone, which is a large area of cloudiness where strong temperature advection is occurring. Both the warm and cold front are located beneath the baroclinic zone. You have the deformation zone, which is going to form to the northwest of the low pressure area in the area of the occlusion. Clouds appear to be wrapping around the low at the deformation zone. The occluded front is found beneath it. And then you have your vorticity comma. That's the last part of the comma cloud on satellite imagery. It's associated with upward vertical motion or rising air motion and positive vorticity advection, PVA. The triple point may actually be located near this area where you get this vorticity comma, and you usually get a lot of unsettled kind of showery precip in that area. And with the mature wave stage of this wave cyclone, the weather is very severe. It's often found at or near the triple point. Poor weather conditions are extensive at this stage. The speed of the mature wave slows down because the amplitude is greatest. Slow movement leads to a decrease in the tilt. at the surface between that surface low and the upper level support, the shortwave trough aloft. So what happens over time is the upper level shortwave catches up and overtakes that wave cyclone at the surface. And the upper level trough will become vertically stacked eventually with the upper level trough, that shortwave trough, moving directly over that surface low. And then that leads to the decaying wave stage of the frontal waves, where the low pressure detaches from the front and becomes cold core barotropic. That means barotropic, now remember we talked about that in earlier videos. Cold barotropic lows, right? That's a decaying wave for you. Cold, as far as coldest temperatures are near the center, and barotropic, we no longer have temperature advection or air masses mixing. It's the same air mass throughout. And as that low pressure loses its warm air intake, the surface low, that surface wave, it begins to fill and eventually dissipate. And as the parent low dissipates, a new low may form right here along the triple point. Okay? If you get the right upper level jet stream winds, let's say we get nice little jet stream winds here, and we get another jet max in the favorable area of the jet max where the air rises, the left front or right rear quadrant, you actually can get a new area of wave cyclone development or surface wave to develop along the front. If that new low or wave does not form the triple point, frontalysis occurs. Basically, frontalysis is indicative of a weakening frontal boundary and decreasing air mass contrast. So in summary, stable waves, let's just say you get asked tomorrow, hey, what's the difference between a stable wave and an unstable wave? Well, you can tell somebody like, hey, I know this answer. Stable waves have no upper level support. They're not linked to those major shortwave troughs aloft, while unstable waves do have that major shortwave trough aloft for support, that area of PVA, positive vorticity advection ahead of the shortwave trough axis, upward vertical motion. PVA is an indicator of that upward vertical motion, and you have upper level divergence ahead of that shortwave trough aloft. On the mature wave stage, the system slows down, it's most intense, and the front begins occluding. Some of the more prolific blizzards, are associated with the mature wave process of the wave cyclone, This is where this system is crawling. This thing is in no hurry to move. It is dumping just heavy snow, just prolific snow amounts. With the decaying wave, the low separates, that surface low or surface wave separates itself from the front and begins to fill. Using satellite imagery and vorticity analysis is key to identifying the various wave cyclone stages. I want to go back to this diagram again, look what's happening. Ooh, I guess I lost my color here. Hang on a minute. Look what's happening back here, When we have the decaying wave stage, we just have this low decaying back here, the cold core barotropic low. And this is all back in the colder air. This letter C represents colder air. It's just sitting there and dying a slow death, But yeah, those are the different stages. This is all about wave cyclones. This happens so frequently across the United States and Europe in the wintertime. I mean, oh my goodness, this is just some really good stuff. It's really good knowledge to know. I'm hoping you're understanding all the concepts of training videos before this and tying it in with this video. And then, of course, vorticity and thermal or temperature advection. This is money right here, guys. Absolute money if you can understand what's going on with PVA and NVA in combination with temperature advection. What's it going to do to upper level heights? Are they going to rise? Are they going to fall? What's it going to do to my surface pressures, my vertical motion, my stability in the atmosphere? My clouds, are they going to increase or decrease? And then just getting back to, hey, we have differential heating across the latitudes. This differential heating is much stronger in wintertime. You could have a 50 to 60 degrees Fahrenheit difference, let's say from International Falls, Minnesota to Miami on a winter day. You have a very strong temperature contrast. Just take a trip from Florida up to Minnesota in the wintertime and tell me how much different your temperatures are between those 2 points. But this differential heating across those latitudes really forms these pressure systems. They're going to affect warm and cold air in the various regions. We talked about frontal waves, developing along that polar front. And, the Norwegian school, you want to look up something cool, look up the Norwegian School of Meteorology. they liken to some of these weather fronts as battlefronts during the World War. And Pedersen came up with this great rule here, Pedersen's rule, which I covered extensively in my last video, I believe. We talk about different frontal waves. We have, stable waves, we have unstable waves, and so on. This really is huge, okay? For the everyday weather changes we see here at the surface in the wintertime as these storm systems move in and out of our areas. All right, that's all I got for now, everybody. It's great to be back. I hope you enjoyed this training video. And, I got one more training video left, and it's on precipitation. Where is the heaviest rain and snowfall with various synoptic scenarios or situations, okay? We're going to take a look at that, and that'll wrap up the training series for the summer. And then we're going to get into the real-time weather. I've got a video ready to go, La Nina winters, which I'm going to show you temp anomalies and precip anomalies in various La Nina winters going back to 2010. So I'm excited to present that here in the future. We're already approaching September, almost mid-September. It's just crazy how fast time goes. But hopefully you're having a great day wherever you are watching this video. And until next time, take care and God bless everyone.